Hi there, welcome to Chem Coach Powers, and today we're going to be talking about phase changes and phase diagrams. I actually really love this subject because it gives me a chance to talk about dry cleaning. Now, you wouldn't ordinarily think that somebody would get excited about dry cleaning, but when you have a chemistry teacher talking about dry cleaning, it is amazing stuff. So I hope you enjoy learning a little bit about dry cleaning at the end of the day because it blows my mind, and I think it will probably blow your mind too. All right, so let's take a look at our objectives here today. We want to identify the changes in state and the related energy changes. We want to talk about energy with regard to changes of state today. And we want to interpret and explain phase diagrams, describe the role of vapor pressure in the changes of state between a liquid and a gas. Vapor pressure is a little bit different than pressure, so we want to distinguish what that means. And then we're going to define pressure in general. So your criteria, given a phase change such as gas to liquid, you can state the name of the change and whether energy is added or removed in the process. You can identify the triple point, that's a pretty cool thing, and the normal melting and boiling points on a phase diagram. And you can explain the boiling point of a liquid in terms of its vapor pressure. All right, so let's look at our changes of state. So first of all, a phase, a part of a system that has uniform composition and properties. Okay, so when we talk about a system here, you can just imagine like an enclosed environment of some sort, right, that we can just measure things with. And so a phase is going to be something that has uniform composition and properties. So imagine liquid water would be the phase, and you could have solid water, and you could have solid and liquid water together, but the phase that is uniform, the part that has a uniform composition and properties, might be the water part, versus the solid part would have its own phase, its own composition and properties. Okay, so when we talk about phases of matter, we're talking about something that has a distinguishable composition and property that is unique from another phase of that same matter. Okay, does that make sense? So solids, liquids, gases, they're all just a little bit different from each other, right? All right. Now let's talk about equilibrium. Now, equilibrium is a condition in where you have two opposing changes occurring at equal rates. And so imagine if you had water at 0 degrees Celsius. Now in your mind, you're thinking immediately, oh, 0 degrees water, that is got to be freezing, right? That's your original inclination, is to think of 0 degrees Celsius as the freezing point. Well, it's also the melting point. And so at 0 degrees Celsius, if you had standard atmospheric temperature and pressure, right, then you would end up having both melting and freezing taking place at the same time, and that's equilibrium. Okay, so there is change occurring, but there's no net change occurring when you are in equilibrium. So here you can see that same kind of thing might be said of a liquid turning into a gas. Now notice that some of these arrows are pointing up and some of these arrows are pointing down. Once you hit this equilibrium point, you're going to have an equal number going down as they're going up. Okay, in other words, an equal number is turning into a vapor as are turning into a liquid. Okay, so now you're at a system which is in equilibrium. Okay, and we call this a dynamic equilibrium because there's something happening there. It's dynamic. Things are happening and taking place, but we're happening at the same rate, and so it's a dynamic equilibrium. And in this case, kind of like somebody going up an escalator that's going down, right? It's a down escalator, and he's just going up, so he's kind of staying in the same place, but he's working hard. All right, so let's talk about phase changes. Again, this is a review for you. Solid to liquid is melting. Solid to gas, sublimation. Some of you might not remember that one. Liquid to solid, freezing. Liquid to gas, vaporization. Gas to liquid, condensation. And gas to solid is deposition. Some of you guys might not know that one. Okay, so a gas to a solid is called deposition. When I was in school, believe it or not, they taught us sublimation was the same term that you use for solid to gas and for gas to liquid. It was in my textbook, and I thought that's the stupidest thing in the entire world. Can't scientists come up with a different name? And thankfully, now we have one that I get to teach you, because I would be annoyed if I had to teach you sublimation for both of them. Okay, let's talk about energy changes. What kind of energy changes are involved with each of these? Now, some of these are a little bit unintuitive, and some of them are very intuitive. But you just take the intuitive one and you reverse it, and you can figure it out, even if it seems unintuitive. In other words, in order to melt something, you could intuitively would be able to figure out, oh, well, yeah, you have to add energy to melt something because it's going to have to heat it up and it's going to turn it into melting, right? Well, again, think about what's happening to the actual particles. you're going from these solid particles that are not moving around very much at all, right? And then you get to a point where they are moving around more in the liquid state, right? And so you're going to have to add energy to them in order to get them to move around more. Well, so if this is what we would consider an endothermic, okay, because it has to absorb energy. If that's an endothermic process, then you have to think, well, the opposite of melting is freezing, which means this is an exothermic property. Now, this is the part that's a little bit unintuitive, because now you're thinking of freezing something, and freezing something actually gives off energy. Yeah, it does. In fact, it's actually kind of cool because let's say you're in an orange orchard, all right, and you're about to have a freeze for the night. What would you do to try to save all of your oranges if you're going to have a frost that night? And if you have frozen oranges, that's not going to be good. What would you do? Well, believe it or not, instead of covering them up with blankets, which sometimes they do, or putting giant heaters in the middle of the orchard, which sometimes they do, the simplest and maybe the most effective, but probably definitely the cheapest, if not the most effective, is just to take and spray all your trees down with a lot of water. You're like, well, that's going to cause them to freeze for sure. Well, but remember that water is moving around fast, right? So these liquid particles in here are moving around pretty fast. And if you can get them to the point where they freeze and they're not moving around anymore, they're just kind of stabilized, then that means that they have not as much energy as they had before, which means that energy had to go somewhere. Where did that energy go? It's an exothermic reaction. And if I had a little orange, okay, if I had a little orange on a tree there and I put some water on it, well, guess what? That water is going to put its energy into the orange, right? Some of it's going to go up here into the atmosphere too, right? As it freezes, but it's actually putting its energy into the orange. And so it actually warms up the orange to pour this water on it as it freezes. Wild, right? Isn't that cool? And so you can actually save, of course, if you had a long freeze and it was a freeze over days, and probably not going to have any chance there. But if you had an overnight freeze and you were trying to protect your oranges for the night, you could spray water on them and that would put energy into the oranges. Isn't that awesome? All right, so same kind of things you want to think about, all right? You have to think about what's happening. If I am going from more energetic to less energetic, then it's going to be exothermic. Okay, and so if we think of the process of solid to gas versus gas to solid, right? So a solid is going from less energetic to more energetic, and so I must have to put energy in that thing to get it going. All right, if I go from a gas to solid, that means it is slowing down big time, which means it's got to give off a lot of heat, right? So that's got to be exothermic. And so you can think of the same thing with vaporization and condensation, right? A liquid going to a gas, that's got to get more energetic, and so that's going to be endothermic. Whereas a gas turning into a liquid, it's going to slow down, and so that's got to be exothermic. Okay, so those are the energy changes that take place in these different phase changes. Again, some of them are intuitive, some of them are not, but you can remember which is which, I'm sure, if you just remember the opposite for the intuitive one. Okay, so now pressure, you've learned many times, you learned it in physical science, but pressure is basically the force exerted over a particular area, right? So force divided by area is pressure. And this comes into play with gases, all right? Because gases are making collisions. And so that collision is creating a force, right? If something collided with you, that's a force, you're going to feel that. And so the more collisions you have, the more force you have, the more pressure you have. And so gases can exert a lot of pressure. Now, how can we, whoa, what in the world just happened? I love it when that happens. Oh my goodness. All right, I'm right there. Come back to me. All right. I don't know what's happening to my world. All right, so pressure can be measured in various different ways. We can measure pressure in torrs. One of the guys that came up with the first barometer, which measures pressure, was called Evangelista Torricelli, right? He was an Italian, and so they named one of the measurements after him. Atmospheres, millimeters of mercury, because they have like little containers, and they have a little tube of mercury, and that mercury pushes its way up the tube. That's kind of the way that they measure it. So you can see how many millimeters it goes up the tube is going to be the value that you would have for the millimeters of mercury for the pressure. Torr and millimeters of mercury basically end up having the same type of numbers. 760 torr believe it or not, is equal to 760 millimeters of mercury, which is equal to 1 atmosphere. But typically in the SI system, we actually use something else. In the SI system, we use kilopascals, okay? So we'll say kPa, kilopascals is the typical measurement that we use, kilopascals for pressure in the SI system. So we can measure air pressure with looking at how many collisions these guys have. Okay, I think I just figured out what was making it do what it did. All right, so let's look at equilibrium vapor pressure. Okay, so if you look at these little containers here, we've got some containers that have some air particles in them. Now notice that this one is closed and this one is open. So the particles are able to escape here, but they're not able to escape here. Now vapor pressure is that pressure that is exerted by the liquid. Okay, so this liquid is having particles fly out, and those little particles are causing collisions on the inside of the container. And so that vapor pressure is what the particles are going to be contacting or colliding with the insides of that container. And so if I have a really volatile liquid, a liquid that evaporates really easily, like a gas or something like that, gasoline, let's say, then you're going to have a higher vapor pressure. Whereas if you have something like mercury, which doesn't allow many particles to escape at all, you have a really low vapor pressure, okay? So volatility is a measure of how easily something, a liquid is going to evaporate, all right? So highly volatile is evaporating a lot. Doesn't necessarily mean it's explosive, right? Volatility, we think of, it's explosive. Not necessarily. It depends on if that substance is flammable, right? If it's gasoline, then a volatile gasoline is definitely going to be explosive, right? But the volatility of water doesn't say anything about its explosiveness, right? So what does volatility depend on? Well, it does depend upon the temperature. If I increase the temperature, I'm going to increase the volatility. Why? Because I'm speeding up these particles and they're moving around a lot faster, right? And it's also going to depend on the intermolecular forces. So again, mercury, which is really cohesive, is not going to have a high volatility. Water, okay, it's going to be more volatile, but gasoline, alcohol, those things will be much more volatile because they don't have as much cohesive properties, and so they're able to escape easier. Because remember, they have to overcome the forces of all the other water particles that are in here trying to hold on to them, right? So those particles have hydrogen bonds with them, and they're trying to hang on. And so in order to get out of the liquid, they've got to overcome those intermolecular forces. And so intermolecular forces can affect volatility and the equilibrium vapor pressure, okay? Remember that this critter right here, this beaker, is not going to reach equilibrium because there are no particles, well, not no, but there are very few particles going back in. Notice most everything is going out. This one can reach equilibrium because particles are going in and out. After a while, that closed container is going to reach equilibrium. But the one on the right is not. In fact, the one on the right is just going to keep evaporating and evaporating and evaporating until there's nothing left, right? All right, so why does this matter? Well, it helps us to understand the boiling point definition. We can actually decrease the boiling point from 100 okay, degrees Celsius all the way down to nearly 0 degrees Celsius. We can basically boil water at the freezing point of water if we pay attention to this volatility, right, and into the equilibrium vapor pressure. So when we talk about boiling point, we always have to talk about the pressure of the atmosphere that is pushing down on it. If we do not accommodate for that pressure of the atmosphere, then we can't really tell you what the boiling point is. So here in Colorado, our boiling point is going to be a lot lower than the boiling point in California. In California, they got more air on them because they're lower down, and so the boiling point is 100 degrees Celsius, standard atmospheric temperature and pressure. The pressure is 1 atmosphere. The boiling point is going to be basically 100 degrees Celsius. But here in Colorado, we're actually closer to 95 degrees Celsius is a closer boiling point for our water because we're a mile high, and at least in the Denver area. And so we actually have less atmosphere. Our atmosphere is not as big, okay, because we're up higher, so there's not as much stuff stacked on top of us. And so it doesn't take as much of the vapor pressure, doesn't take as much of the pressure from here to escape. All right, so it doesn't take as much pressure to escape. And so the temperature doesn't have to be as high to get the particles moving as fast as they would need to move to escape and get out, okay? So that's why. All right, so that matters for the boiling point definition. So again, our boiling point is going to be the temperature at which equilibrium vapor pressure is equal to the atmospheric pressure. And so notice here, I've got air at 760 torr. My water has been heated up. It's 90 degrees Celsius down here, right? And so it is at 525 torr. That's not high enough to boil. Finally, I get to 760 torr, which is equal to that. So now I've got them equal to each other. So now you can see there are more particles flying out. Finally, if I get the water, and it's going to stay at 100 degrees Celsius atmospheric pressure, this is all eventually going to evaporate, right? And it's boiling away at this point. But if I were able to get that water above 100 degrees Celsius, okay, and I only had 760 torr here, and the water's pressure, vapor pressure was really high, then it would boil really fast, okay? It would just boil faster, basically. All right, so temperature is going to remain constant during boiling. That's really important to remember, that your temperature doesn't rise. And the reason for that is because all of the energy is going into converting that liquid particle into a gas particle. It's going into breaking those hydrogen bonds between the water molecules and allowing them to escape. So all of the energy goes into breaking hydrogen bonds. So this temperature doesn't rise above 100 degrees Celsius, right? It's going to stay at 100 degrees Celsius until all that stuff is boiled out. Now, you might have certain localized areas which are not the same temperature, but if you're stirring this thing, it should all be pretty uniform. All right, let's talk about the freezing point. Okay, the temperature at which solid and liquid are at equilibrium is called the freezing point. And again, pressure does not have nearly as much of an effect on freezing point as it does the boiling point, but it does still affect it a teensy bit. All right, so what's happening here? Again, the same idea. You've got water becoming ice and ice becoming water, right? The arrows are going in both directions at 0 degrees Celsius. But what's going to happen if we lower that temperature? If we lower that temperature, then things are just going to go mostly in one direction, right? It's going to be all turning into ice, and very little, although still some, would be turning into the water. Now, and I say some because particles are always in random motion. Remember we talked about how even solid particles can sometimes diffuse and turn into a gas. And so these particles are still moving, and every once in a while one gets enough energy to jump out. But for the most part, the direction is in the ice direction, and it's not at equilibrium anymore. Remember, equilibrium is equal amounts both sides. That would not happen if you got it below 0 degrees Celsius. All right, remember the temperature remains constant during the freezing and melting process. And so if I were boiling, if I were heating up, let's say I had a beaker of ice water. And so here's my water, and I got a bunch of ice cubes in here. If I had a bunch of ice cubes in that little beaker and I was heating that thing up with some flames, you would actually see that temperature, if I could stir it well enough, that temperature would stay at freezing, right? It would stay at 0 degrees Celsius until all the ice had melted. Once all the ice had turned into water, then that temperature is going to start to rise. But it's not going to rise until all of that ice is melted, okay? Again, why? Because the added energy is going to be used to separate the particles, okay? Or to look at it the other way around, the removed energy would be bringing the particles together if I were trying to freeze this. Okay, so now on to phase diagrams. Again, phase diagrams, awesome. I'm going to talk about dry cleaning pretty soon, which is really great. Trust me, it's cool. All right, so graphs of pressure versus temperature that show the conditions under which the phases of a substance exist. Okay, a couple terms we want to make sure that we identify here are triple point. This is where all three phases can coexist. So you have solid, liquid, and gas all existing at the same temperature and pressure. Way cool. Then you have critical point. Now, critical point is the critical temperature and pressure, and this is the point at which the liquid, okay, doesn't exist. There is and I'll show you here on the graph in a second, but there is a new, it's kind of like a new phase, a new reality that exists for the substance above the critical point, okay? And so you will not have a liquid above the critical point. And again, the normal boiling point is at 1 atmosphere of pressure, and it's the temperature at which it's going to boil at 1 atmosphere of pressure. The normal boiling point is that. The normal melting point would be the temperature at which it would freeze or melt at 1 atmospheric pressure. Let's talk about the density of the solids versus the density of the liquids with regard to the phase diagrams. Remember that water is kind of unique from most things, but this little slope of the line is important to pay attention to. So pay attention to the slope, because you can derive some information from the slope that has to do with the density, okay? So before I go into that, let's just talk about this graph in general and see what it means. So first of all, I've got a solid here in the purple area, a liquid in the yellow, and a gas in the green. What does all that mean? Well, it's basically a way to measure temperature and pressure, okay, of these substances as they're going. Let me erase this little stuff right here, get it out of the way of the pressure. And notice I've got temperature on the x-axis, pressure on the y-axis. Okay, so what happens, imagine yourself as a solid. Okay, I'm going to imagine myself as a solid right here. And if I just increase, so my pressure is going to stay the same, I'm just going to go across the line in this direction. If my temperature increases, I'm going to get to a point where eventually I turn into a liquid. Right as I cross this line, that is the line at which I turn into a liquid. So you should recognize that line, right? That line is called melting. Or if I were going in this direction, it would be called freezing, right? So this line is a melting / freezing line. If I'm a liquid and I keep going in this direction, well, I kind of should not be at the critical point. And I were to go into the gas, which is the green area, then that would be the point at which I am boiling, right? Or vaporizing. So here, this line is going to indicate the boiling / vaporization line, and then the condensation line, where it's going to go from being a vapor back into a liquid, if it's going back in that direction, right? And so boiling would be going across the line that way, condensation would be going across the line that way. And so these lines are indicating the threshold of the different phases, and that's why it's called a phase diagram. Now, the critical point, let me kind of erase some of the junk I wrote right over that critical point because it's kind of in the way. Notice how in this graph, I do not have the same color. I do not have the same color above the liquid. It has this point right here. Now, remember we said that above this point, it's the temperature and pressure, okay, that exists right here. At that temperature and that pressure, I don't exist as a liquid above this. So there's actually, even though this is kind of showing yellow, there's actually should be no liquid above this point here. Okay, so all in that area up there, okay, all this area up in here, that is not going to be a liquid, okay, even though it's kind of showing yellow. And you're like, well, then it must be a gas, right? Yeah. So it's actually kind of cool because it actually kind of is a multi-phase substance. And here we come into the dry cleaning. It has kind of a unique property, a unique set of properties that are not quite a gas and not quite a liquid. And it's kind of fascinating to study it. And I definitely encourage you to study it even further. There's something called a supercritical fluid, okay? And so basically at this point, we call it a supercritical, fluid. Okay, it's above the critical point, so it's supercritical. It's a fluid, so that's like a liquid and a gas, and it's kind of like both, and it's not like either completely. And here's the cool thing. If you think about dry cleaning, If you think about dry cleaning, how do they make your clothes get clean without getting them wet? Okay, if I were washing your clothes, I'd be here in the liquid phase, right? Well, what they do is they get a particular material, this substance. I have a few different ones that they can use, but they take this chemical and they push it past the critical point. Now, this substance has got some hydrophilic and hydrophobic properties, so it's going to work a lot like soap, and it's going to grab onto dirt, right? And but it also can grab onto itself in a sense so that it can take the dirt and move it away. And so this substance, they get it to the supercritical phase, this beyond the critical point, and then they put your clothes in this room where this stuff is at. And so this stuff is like this fog, this kind of gassy, liquidy kind of stuff that goes in, and then it attacks your clothes, dirt. It grabs the dirt, and then it is able to be vacuumed out, right? Sucked out. And when it sucks out the dirt with it. Okay, so your clothes get clean without ever getting wet because they're in a supercritical fluid, which is more like a gas in this case than it is like a liquid. Isn't that amazing? Did you ever think dry cleaning was so cool and so chemical? But yeah, that's what it is. Okay, so supercritical fluid, awesome. Dry cleaning, awesome. But let's talk a little bit about that density line as well. Okay, so I want to focus in on this line and the slope of the line really quick. So I'm going to erase this little stuff and talk about what's happening here. Now imagine that I am now at a particular point on, well, tell you what, I'll just go ahead and use this one. As you can see, a little D there. Let's imagine that I'm at a certain point right here, really close. I've just melted, so I'm now liquid, okay? I raised my temperature up just enough, but then let's say I'm raising my pressure up. If I raise my pressure up, what happens to my substance? What side of that line am I now on? I am now on the solid side of the line. So here you can see that pressure, when you increase pressure, you can take a liquid and turn it into a solid. And this is what happens with carbon dioxide, right? If you take carbon dioxide, that's dry ice, and you apply pressure to that liquid, you can actually turn it into a solid. Whoa, that's cool, isn't it? So you can take and you can go from a solid to a liquid by decreasing the pressure, right? You can cross over that same line. Now, again, you can see what happens if I keep decreasing my pressure. I'm going to turn it into a gas. Now, notice that this slope, the slope of this line is a positive slope, okay? Notice that. Slope of this line is a positive slope. And it's something a little bit unique and interesting to notice, I don't have it, about the phase diagram for water. If we were looking at the phase diagram for water, oh yeah, and I'm not doing good at drawing this right now, but I would actually see something different, okay? We talked about how water has some unique properties before, but one of the unique properties is that increased pressure for water actually does the opposite, okay? It actually turns it into a liquid. So I could be on this side of the line, here's a solid, and I increase my pressure and I actually turned it into a liquid. Okay, so water works a little bit differently in a few different ways. This is one of the ways. The phase diagram of water would actually be where that solid liquid line is, it'd actually be kind of cutting back a little bit instead of going forward. Again, I apologize for my bad drawing. Let's just kind of do it like this. Oh, whoa, yeah, that's cool. Not what I meant to do at all. Let's just kind of say that that line is right there. I don't know what that came from. Okay, so we learned a lot of good things here. Let's talk about what we've learned, go through it. Identify the changes in state that are related to energy changes. So we learned all those different changes in state, sublimation, condensation, evaporation, all those kind of things, right? Interpret and explain phase diagrams. Yes, so now you've seen a phase diagram, you can understand what they mean and explain them. And then describe the role of vapor pressure in changes of state. Yeah, so if I increase my vapor pressure, I can see different things happening between the liquid and gas, right? If I increase that pressure, I can make more of that liquid go into, or more of that gas go into a liquid form. And so I would need a higher temperature in order to boil things, for instance, right? And then, of course, pressure, you can define that. Force is divided by area. Okay, so let's see. Given a phase change into a gas to a liquid, you can state the name of the change. Gas to liquid is? Very good. So when you are going from a gas to liquid to condensation, right? And that's the name, and whether it's energy added or removed, okay? It went from going faster to slower, and so that means that the energy had to be given off, right? So that's going to be an exothermic process. And this is also, by the way, I was going to say this before, this is where steam burns can be a lot more dangerous than other types of regular water burns. As steam getting onto the skin deposits a lot more energy as it turns into a liquid than just regular boiling water would, because the steam is much more energetic. And so because it's an exothermic reaction, it actually can really cause a lot of damage to your skin. So steam burns are very dangerous. Again, you don't really see steam. One of the things that I always like to point out, you guys may maybe imagine a tea kettle, and that tea kettle, oh, this is not going to be a very good tea kettle. It kind of looks like an elephant. But that tea kettle, you notice that little puff of stuff that comes out, it's all cloudy. Well, that is already back to the liquid state, right? That's actually a liquid at that point. It's a cloud, and cloud is made up of liquid particles. But this part right before the liquid, if you look at that right before, there's this little gap right here. That's steam, okay? That's while it's still a gas, and that's where the temperature is higher, and it's definitely a lot more dangerous. So if you were to put your finger into that little spot right there, that would be a lot more dangerous than putting your finger into that spot right there, okay? Because by the time it's gotten up here to where it's not clear anymore, it's already converted from a gas to a liquid, and it's given off that energy. You can feel that residual energy there. Anyway, another fun little thing about this. All right, so identify the triple point. Yeah, on a graph, you saw that place with all three. Oh my goodness, I didn't even talk about that? What? I did talk about it a little bit, but I didn't really talk about it. I'm sorry. I am a failure. All right, so really quickly, that triple point is the place where, just making sure you're watching all the way to the end, right? That triple point is a place where the solid, the liquid, and the gas all exist at the same temperature. And there's actually a real quick and easy lab that we can do, and we normally do it every year. It's where you take a little bit of dry ice and you put it inside a pipette, and then you heat that, you seal it up so it can't get out, and then you heat that up by just putting it in some cool water. And you'll notice there's a point where, of course, it's expanding as a gas, and then you can see this liquid dry ice. It turns into liquid carbon dioxide, and so you're like, oh, it's liquid carbon dioxide. That's cool. You don't see that very often. And then you can still see some positive crystals too. So you have both the gas, because it's expanding, and then you have the liquid, and then you have the solid carbon dioxide, all at the same temperature and pressure. And you can just create that with a tiny little pipette. So cool. But you can do this with water too. But with water, you'd have to get the temperature down to basically 0, and the pressure's got to be down to basically a little bit below 0. So yeah, that's a triple point. Sorry, I didn't talk about that already. All right, now I've covered. Now you can tell me what triple point is and critical point, normal, melting, and boiling points on a phase diagram. Remember that you'll see those normal points oftentimes with a line, and here it is. Okay, so this line right there, it shows you 1 atmosphere, and so this line right here is a line that's indicating the normal, in this case, the normal melting point or normal freezing point. So you say, oh, well, that's 78.5 degrees, and that goes from a solid to a gas. Now notice that we don't have boiling for carbon dioxide. It doesn't go from a solid to a liquid. Melting, sorry. Let me try this again. So this one is sublimation because it's carbon dioxide. Normally we'd have liquid on this side, but because this is carbon dioxide, we actually have sublimation. And so this is going from a solid to a gas at this temperature. And so this would be our normal sublimation point, but it's really not a normal boiling point, normal melting point, because melting doesn't occur until you get up here, right? And so we don't have melting at 1 atmosphere of pressure for carbon dioxide. We have to get that pressure up to 5.1 atmospheres before we can even start seeing any liquid. And that's where we finally start seeing the melting that might take place. So anyway, hopefully you can see that. I apologize, it was not too clear about that either. Man, off my game a little bit. That's all right. I'm making all these amazing drawings like this cool tea kettle. Okay, so if you're this artistic, you don't have to be too scientific because you're just amazing that way. Okay. All right, so now I can explain boiling point and liquid point in terms of vapor pressure. Again, just really remember to say that the boiling point is going to be, the temperature and pressure at which the vapor pressure and the atmospheric pressure are equal to each other is pretty much the way we like to state that. So you've got to have enough of that vapor pressure so that the thing is going to escape, and that's what's going to allow it to go past and out into the atmosphere, and that's when you finally are out of equilibrium. All right, so lots of cool stuff. I love this stuff. Check out some of the stuff on YouTube. There's some cool videos and all that kind of stuff you can watch about all this. But that's all I've got for you today. We're not going to take too long. We already kept it long enough. God bless you. You have an awesome day, and be kind to one another.